Hello everyone, so today we're going to solve two example problems regarding the drill string fundamentals and the 2D token drag for your next quiz. And the first example, the given is we have a vertical well of 12.25 inch in diameter and 12,000 feet in depth, and we plan to drill plan to use 9.5 inch casing with 10.58 outside diameter coupling, and our circulating mud density is 12 ppg. And if the drill color has an ID of 3 inch and we have weight on bit of 45,000 pounds, and we assume that the friction coefficient is 0.04 if it contests the wellbore. And what we're trying to determine is A, the drill color size and length with the design factor of 1.2, and also during drilling the weight on bit is actually increased to 50,000 pounds, and we try to determine if the drill string will buckle or the total force applied on the bit, and also the tilt angle. So in any procedure of solving this problem, if any iteration is needed, please show 3 steps of iteration. So it's same as the last quiz, same as the old quiz last year. So now let's try to solve it. So first we're trying to solve the drill color size. So with the equation given in the literature, given in the lecture 11, page 8, we can have the outside diameter of the drill color. We can calculate the drill color based on the coupling diameter and also the wellbore diameter. Then just plug this number in, you get 9 inch of the OD of the drill color. And then with the OD of 9 inch and ID of 3 inch, and using the table on lecture 11, page 6, table 9.1, we can actually locate the weight per length of this drill color. And I have the table printed out, so just show you the step. So here is the drill color OD diameter, which is 9 inch, and the ID diameter is 3 inch. Then we can find this one, the WDC, which is the weight per foot of the drill color, is 192 pound per foot. And then the buoyancy factor is 1 minus rho mud divided by rho steel. And also this equation is to calculate the length of the drill color. And we can have this equation from page 9 of the lecture note. Just plug the number in. Because it's a vertical well, so the angle here is 0, which cosine 0 will be 1, and you get the drill color length 344.3 feet. And at this in this calculation, we assume the steel weight is 65.5 ppg. So that's how we solve the first problem, the drill color size and the length, with the design factor of 1.2. The 1.2 here is the design factor. And the second problem is to calculate the if the drill string is buckled when we have weight on bit up to 50,000 pounds. So first we need to calculate the moment of inertia, which is pi over 64 times the OD of the drill color minus ID of the drill color to the power of 4. And this 12 is convert the inch to the feet. So now we get this one in feet to the power of 4 in unit. Then the P is basically just the buoyancy weight of the drill color in the drilling mud. Then you just plug this number in with the buoyancy factor, then you get this buoyancy weight of the drill color. And M is dimensionless parameter. You just put the E, I, and the P. Just plug the number in, and here we assume the drill color with E of 4,320 to the 10 to the power of 6 pound per square foot. Now you get this number 75.04 for the M. Now just plug the number back to the buckling criteria, which is the first order buckling. You get 1.94 P times M, and just plug the P and M just calculated, which is P equals to 156.8 and M is 75.04. Then you can get the first order buckling criteria, which is 22,831.61 pound. And the second order buckling with this equation, all these equations you can find from the lecture PowerPoints, and if you're more interested in that, you can look through the book, the textbook, and have more information about this. So 3.75 PM times 3.75 times the 156.8, which is the P, and the 75.04, which is the M. You get the second order buckling. So if we have a weight on bit of 50,000 pounds, it's greater than the first order buckling, and it's also greater than the second order buckling. So which means our drill string under this weight on bit will be in the condition of second order buckling. So to the second question, and the answer is yes, and the buckling is the second order buckling. So that's the second problem. So the next problem is the total force applied on the bit. So now we need to do the calculation to first determine the distance to the neutral point, which we assume that there's no friction at the beginning, because we don't know how much force we applied, so we need to solve this problem iteratively. So first we assume that there's no friction, and with this equation you can calculate the length to the neutral point, which is 50,000 minus 0 divided by P, 156.8. You get 318.9 feet. And the dimensionless length is this length we just calculated here divided by the M, 75.04. You get 4.25. So with this one, you will need to find out from the table 4.9. You can also find the table, find the graph, the figure in the lecture notes, which is the one here. Okay. So basically, our dimensionless length is 4.25. It's actually here. We go up, and it's somewhere up to here. Then you cross to get the reading. This pen is out of ink. Okay, sorry about that. So we go upward to this point, and you read this number. So it's close to, this right here, close to 2.7, which we can find that the coefficient F is 2.7. Then use this equation for the side force at point of tangency, N equals to FPR. The F is 2.7, which we just find out from the figure, and the P is the buoyancy weight 156.8, and R is the is the apparent radius of the hole, which is which is this one, 0.5 times the clearance, which is the diameter of the wellbore in feet minus the outside diameter of the drill color in feet. Now you get this number, so you just do the calculation. You get the side force 57.33 pound. And then we can calculate the friction at the contact point, because we from the given we know that the friction factor is 0.04, and we times the side force which applied toward the wellbore, and you get the frictional force 2.2932 pound. And so if we have a friction force like this, our length to the neutral point should be recalculated by plugging the friction force in here. Then we just redo the calculation. We get the length to the neutral point 318.8629 feet, which close to the one we just calculated. And we do the dimensionless length 2.249, and from the figure it's also, sorry, not this one, from the figure it's also about 2.7. So now we just use 2.7 to calculate again our new friction force is also 2.2932 pound, which is the same as the first iteration, which indicates that if we do the third iteration, we'll have the same answer. So which means our side force is equal to 2.29 pound. And now we need to find out what's the inclination of the force on the bit, because this is the side force at the tangency, right? So now we just use this equation, which you can also find it from the lecture note, and from the figure 9.3 we can find that n equals to 0.5, which is 9.3. The figure is here. It's on the page 19 of the lecture 11 PowerPoint slide. So we know that x2 4.249. So it's about here, and it go all the way up. So this is for n, and you just cross this to get n, to read n. The coefficient n will be about 0.5, right? So now we know that n is 0.5, so you plug the 0.5 here. The r is the same thing, just 0.5 times the wellbore diameter in feet and the drill color outside diameter in feet, and divided by this m, which we calculated previously, 75.04. You get the inclination of the force on bit in radius, right? It's 0.000902 rad. And now you need to calculate what's the side force on the bit. So it's basically just using this equation, which also provided on the lecture slides, but it's in another form. You just put the h0 on this side, and you get this, and this is the weight on bit. The actual weight on bit is 50,000 pounds. So this one times the tangent of the inclination, you get the side force 45 pounds. Okay? So now we need to calculate the total force, which is also called the resultant force, and it's just the combine of two forces. One is point downward, the 50,000 pound weight on bit, and the other one is the side force for 45.1 pound. And just do it like this, and the square root of the square of the sum of two squares, and you get 5,000.02 pounds. Is basically the same as the weight on bit because the inclination is so small, 0.00902 radius. Okay. So now this is the total force. So we get our solution for the question C, which is the total force acting on the bit. And our last question is to calculate the tilt angle. With tilt angle, the beta is just equals to T times R over M. And T from the table 9.3, I just showed you before here. So also we'll also find out that the x2 to the neutral point is 4.249, the same thing here all the way up. And you find this curve is for t, this curve is for n, and for t you get the t is almost 1.5 ish, right? So plug 1.5 here, and r is the same thing, and plug the number of m you just calculated, you get the tilt angle 0.00271 raise, and the translate into degree is just 0.0155.